Bismillahirrahmanirrahim. So, a quick recap of the last thing that we studied regarding the propagation, and that was actually related to uh, the freeze equation. So, let me give a quick recap, especially related to uh, these units that are very important actually, right? So whenever we talk about SNR, SNR is basically the power in the signal divided by power in the noise, right? So that is basically a ratio. So whenever there is a ratio, it means that it is a unitless entity, right? So signal power divided by noise power, it means SNR is unitless. But we can convert that to logarithmic unit. So 10 log base 10. For example, if we get this answer in, for example, x, right? So if we take the 10 log base 10 of this, we will get the SNR in dBs. SNR in dBs. So dB basically is not the unit of power, rather dB is a unit of SNR, and that is a ratio. So people usually get mistaken and they say that dB is a unit of power. No, dB is a unitless entity, right? So SNR is the signal power divided by the noise power. And since both of the entities are same, for example, watts divided by watts, X is unitless. So that as X, when converted to the logarithmic unit, we will get the SNR in dB. And therefore, dB is not the unit of power, right? But for example, we have something in X watts. So if we take the 10 log base 10 of this X, we will get this X in dB watts. So this is the answer that we have just got. This is in dB watts. This is a unit of power. This is a unit of power. Just as watts is a unit of power, similarly, dB watts is a unit of power. Similarly, if we have X in milliwatts, if we have X in milliwatts, right? So if we have something in milliwatts, it means if we convert that 10 log base 10, and this X is in milliwatts, we will get the answer in dBm. So dBm is again a unit of power. dBm is a unit of power, dB watts is a unit of power, but dB is not the unit of power. So dB is not the unit of power. This is a very common mistake that people do. The dB is not the unit of power. dB is actually the ratio. And similarly, dB watts is a unit of power. dBm is a unit of power. And there is one relation between dBm and dB watts, and that is if you add 30 to dB watts, you will get the answer in dBm, right? So you will get the answer in dBm. So for example, you have something in watts and you want to convert that to milliwatts. So one method could be that you write that X in the form of milliwatts, for example, into 10 power minus 3. Or the other idea is to just get the answer in dB watts and then just add 30 to that, right? So you will get the answer in dBm. So these were few of the things that were important, right? So let's move on to our topic. Polarization. When we say polarization, electromagnetic waves are generally polarized. They have got instantaneous electric field components in orthogonal directions in space. It can be mathematically represented as a sum of two orthogonal components, such as vertical and horizontal. Polarization can be used as a degree of freedom for frequency planning. So why we are talking about polarization? Basically, it's all about the electrical field intensity. Electrical field intensity. So this is a vector basically. So what electrical field intensity tells us, it tells us basically about the force over charge. the force over charge. So basically, as you know that electrical field intensity is a vector, it must have some direction. So if the direction of the electrical field intensity is horizontal to the Earth's surface, so that would be a horizontal polarization. And if the direction of the electrical field intensity vector is vertical to the Earth's surface, that would be vertical polarization. But why we are talking about this? Because in case of any kind of propagation, the electrical field intensity is perpendicular to the magnetic field intensity, and that is perpendicular to the direction of the propagation. So all of these things are basically orthogonal to each other, and that is why polarization has quite a bit of significance. Basic propagation mechanisms we will talk about is related to basically reflection, diffraction, and scattering. But first, let's see reflection. Reflection occurs when electromagnetic wave impinges on an object having a very large dimension compared to the wavelength. As you know, the wavelength is inversely proportional to the frequency. And what we want is that the object is having a very large dimension. For example, the surface of the Earth. For example, building, walls, these are big surfaces. So reflection usually occurs from surfaces that are big. Diffraction occurs when the radio path is obstructed with object having sharp irregularities. For example, edges. So these are not big surfaces, rather we are talking about the edges or surfaces that have kind of irregularities. So this explains radio propagation without having a line of sight. Depends on the geometry of the object as well as frequency, phase, amplitude, and polarization of the incident wave. So these are the things that are dependent upon that. And next we have scattering. When we talk about scattering, this occurs when the environment has objects with dimensions that are smaller or comparable to the wavelength of the incident wave, and the number of objects per unit volume are quite large. For example, in a practice foliage, street signs, lamppost, these are few of the examples. You may come across the phenomenon of scattering. Scattering would be more perceptible. By perceptible, I mean able to be seen or noticed to a millimeter wave rather than the microwave. So scattering is more pronounced for a frequency range which is very large. When you have a large frequency, it means the wavelength is very small. So if the wavelength is very small, the scattering is more pronounced. So you need to remember these things. First, reflection is for large surfaces. Diffraction is for surfaces that have irregularities. And again, scattering is for the objects that are very small, and so that the wavelength is quite smaller, and that is why it is more perceptible in the millimeter wave range where the frequency is very high. Millimeter wave range is the one that has a frequency that is very high. So in that case, the corresponding wavelength is very small. So let me tell you a little bit about the millimeter wave. Millimeter wave band is the spectrum where the wavelength is between 10 millimeters and 1 millimeter. So as you know, when we are living in the age where we are talking about 5G and 6G systems. So you come across applications that desire a very high frequency. So millimeter wave is quite a common terminology, especially in the 5G era. So in the millimeter wave range, the frequency is between 30 gigahertz, which is huge, but between 300 gigahertz, which is even more huge than that. So this is a quite, significantly high frequency. Since this is a significantly high frequency, the corresponding wavelength is in millimeters. And that is why the name stems from this, that millimeter wave, a band which has a very high frequency. These frequencies are called millimeter waves because they have wavelengths between 1 millimeter and 10 millimeter, while the wavelengths of the radio waves currently used by smartphones are mostly several dozen centimeters. So far, only radar system satellites use millimeter waves, but recent applications of automotive communication, they are also communicating in the millimeter wave range. And ever since 5G is getting evolved, millimeter wave is quite a common band for applications that are in 5G. Okay, let's dig in deep into reflection. Reflection occurs when the electromagnetic wave impinges on an object having a very large dimensions compared to the wavelength. We have just talked about this. It occurs when the two media have different electrical properties. If the medium is a perfect conductor, all of the energy is reflected back without any loss of energy. For a perfect dielectric, part of the energy is transmitted into the medium and part of it is reflected back. Electrical field intensity of the reflected and transmitted wave is related to the incident wave in the medium of origin through Fresnel reflection coefficient that we're going to see shortly. So this is the reflection from the dielectric. This is the electrical field in the plane of incidence. So you can see that this is the electrical field intensity. This is the corresponding magnetic field intensity, and this is the direction of the propagation. As you know that all three of them should be perpendicular to each other. So in this one, electrical field intensity is in the plane of the incident. Electrical field intensity is in the plane of incidence. This is the plane of the incidence, right? This is the incidence angle and this is the reflection angle, right? So you can see that electrical field intensity is in the same plane as this plane of incidence. And as far as B is concerned, electrical field intensity vector is into this. You can see that dot. This means that is into this, your screens, or if you take a printout of that, you can say that into the page. So electrical field intensity in that case would be normal to the plane of incidence. In that case, this H is in the plane of incidence. So these are the two different scenarios. So in this case, you can see that epsilon 1, mu 1, sigma 1, this denotes the permittivity, permeability, and conductivity of object A or the surface A or the surface 1. And this means epsilon 2, mu 2, sigma 2, the corresponding electrical permittivity, magnetic permeability, and conductivity of material 2. And similarly for this B as well. So we usually talk about electrical field intensity and electrical permittivity and magnetic permeability. And also we also memorize the corresponding coefficients for them or the values of them for free space. But we need to know what exactly is the meaning of that. So the ability of a material to store electrical potential energy under the influence of an electrical field measured by the ratio of the capacitance of a capacitor with the material as dielectric to its capacitance with vacuum as dielectric. Is it an easy definition? I don't think. Yes, let's wait. The permeability is the measure of the ability of the material to allow the formation of magnetic lines of force or magnetic field within. It speaks on the ability of magnetization that a material possesses for the applied magnetic field. A somewhat better definition. But electrical permittivity, as you say, permit usually means you allow something to pass on. So when you say electrical permittivity, that is basically measure of how much electrical field the device or the object allows to pass through it. This is the meaning of the electrical field permittivity. And similarly for the magnetic permeability, it means how much the material is able to absorb the magnetic field across its surface. This is basically the meaning of the electrical permittivity and magnetic permeability. And we have another ratio, this eta, that is basically the ratio of permeability to permittivity. And this is also known as the characteristic impedance of the free space. This is also known as the characteristic impedance of the free space. The two formulas that you see on your screen is basically the values of the reflection coefficient between the two dielectrics corresponding to this electrical field in the plane of incidence and the reflection coefficient corresponding to electrical field normal to the plane of incidence. Okay, next we have Snell's law. Again, it relates the two materials and we can get the corresponding angle of incidence and the corresponding angle of reflection from the Snell's law. And Another important thing is Brewster angle. It is the angle in which no reflection occurs into the medium of origin. It is given as this. So this is the relationship of that. This angle signifies that particular angle at which there is no reflection in the medium of origin. So everything just gets passed through to the next material. That is known as Brewster angle. Next is the diffraction. Diffraction allows radio signals to propagate around the curved surface of the Earth, beyond the horizon, and behind obstructions. So as we see that in our daily lives, we see a lot of constructions going on around. So obviously these are buildings. These are not, building material is not something that allows the electrical signal to pass through it. So obviously we come across all these phenomena of reflection, diffraction, and scattering. So this is caused by the propagation of the secondary wavelets into the shadowed region. So shadowed region is the one which is not in your line of sight. So this is based on the Huygens principle, which states that all points on the wavefront can be considered as point sources for the production of the secondary wavelets, and these wavelets combine in the direction of propagation to produce a new wavefront. So this is kind of repetitive process. I have explained a bit of these wavelets after a few slides, just for those of you who are not very comfortable with this wavelet thing. The field strength of the diffracted wave is the sum of the electrical field components of all secondary wavelets in the space. So let me talk about this wavefront first. So wavefront is basically a surface or a line in the path of wave motion in which the disturbances at every point have the same phase, right? So depending upon the source of light, wavefronts can be of three types. They can be spherical, they can be cylindrical, and there can be a planar wavefront. So just imagine you throw a pebble into the water. So you will see wavefronts. You will see wavefronts. So if you throw a pebble and after a little while you throw another pebble, you may get a direction from this. You may get a direction. You see a uniform direction, but depending upon how you throw the pebbles into the water, I will talk about this phenomena when I will tell you about the beam forming, just to give you an idea that what a wavefront is right now. So I think that would be enough. Next is the scattering. Scattering occurs when the environment has objects with dimensions that are smaller or comparable to the wavelength of the incident wave, and number of objects per unit volume are large. That we have studied a little while ago. In practice, foliage, street signs, lamppost, these are a few of the examples that can cause scattering. It would be more perceptible to a millimeter wave rather than the microwave that we have also seen a little while ago. It follows the same principle as diffraction, and it causes radiations in many directions. So let's see this example. You see this car, right? So for example, it has some kind of radio device or a mobile phone, right? And it is transmitting something. So let's suppose that this is a building. So because of this building, it will cause a phenomena of what? Reflection. Because this is a very large surface, it will cause reflection, right? And this edge can cause diffraction. This edge can cause diffraction. It can be an edge of a big surface or even from a small surface, but again, the condition of diffraction should be fulfilled. And as far as the smaller objects are concerned, for example, a lamppost, a traffic signal, or you can say some kind of advertisement signboard, it can cause scattering. It can cause scattering. Real life scenario, all three mechanisms play a role in the received signal strength. In case of a line of sight path, diffraction and scattering do not dominate the propagation or the received signal strength. If the mobile does not have a line of sight, then diffraction and scattering would probably dominate the propagation. Because, for example, it has to communicate with someone over here. So reflection may not play a very significant role in that case. Scattering and diffraction play a significant role in order for the signal to reach the shadowed part. Shadowing. The reason for shadowing is the presence of obstacles like large hills or buildings in the path between site and mobile. So this is a mobile phone, this is a building, this is a mountain, this is the base station, right? So shadowing is because of the presence of large objects, which can be buildings or mountains or whatever. A very important graph that you see on your screens, this is basically showing you the relationship between the received power, or here there is, that is not the power, this is the dB, this is the ratio of received power of the or the transmitted power. So when I say this is also showing us the power, obviously we have a power in this, so from that we can say that since the power of the receiver is in the numerator, so obviously as this graph will go down, it means the received power is also going down, right? So in that case, you can say that this is also showing us the power, but overall, this is a graph of the ratio of powers, and therefore it is in dB. And on the x-axis, you see the distance. On the x-axis, you see the distance. So as you move away from the transmitter, or as the distance between the transmitter and receiver is increased, the corresponding received power also gets decreased. Yes, then you have also seen this in the freeze equation. So the distance was in the numerator. The distance was in the numerator. So let me just quickly show you the freeze equation again. So distance was in the numerator, right? So if you're plotting the received power of, or this PT goes on the left hand side, so obviously that would be the ratio of power. In either case, as the distance is increased, the corresponding received power or the ratio of power will go down. And therefore, as you can see over here, that as the distance is getting increased, the received power is also going down. But for the case where there is only path loss, we say that you only have path loss. You are getting loss in the power because of the path or because of the distance. But if the path loss is also accompanied with shadowing, if the path loss is also accompanied with shadowing, that is, you're going away from the transmitter, but also there is a case of shadowing. So this line would not be straight in that case. That would not be a completely linear line. It can go up and down. But if there is shadowing, path loss, and also multipath, this is very important. So whenever we say multipath, it means from the multiple paths, you're getting the signal. So for example, if I transmit from point A like this, right? And this is a point receiver. So this is a transmitter and this is the receiver. So you're getting the signal over here from this or this or this. So you're getting the signal from multiple paths. You're getting the signal, the same signal. You're getting the same signal from the multipaths. So if there is path loss and shadowing, and on top of that, there is also multipath. So in that case, the received power will fluctuate further. In that case, the received power will fluctuate further. Obviously, if we just interpolate this or, do a simple linear regression, obviously we will get this straight line. But in reality, this is only for the case when there is path loss alone. When that is accompanied with shadowing and multipath, you will get a graph like this. Okay, next thing is the small scale for propagation. The small scale fading, in the last lecture, we have also seen that small scale fading is normally encountered when we travel for a very small distance and we get degradation in the signal. This usually occurs because of two things. One is the multipaths and the other is the motion of the receiver. So these are the two biggest contributors of this. So you can see this car, there are a lot of multipaths in that, and also the motion of the receiver. So these are the two things that cause small scale fading. Wireless channels are multipath propagation channels. So at the receiver, the different copies of the same signal would reach. You don't get the signal only once, or it's not very simple. At the receiver, you get different copies of the same signal with different directions. You can see here, for example, if the receiver is over here, it is getting signal from different directions, different propagation delays. Obviously, for example, some signal has to travel a lot of distance and then it reaches the receiver. It will obviously be a delayed signal, different amplitudes. A signal, a direct line of sight signal obviously has a greater amplitude, but a signal that has undergone multiple paths, obviously the amplitude of that would be lesser than the other signals. So different directions, different propagation delays, different amplitudes, and therefore obviously different phases, and different angle of arrival. So all these effects cause the phenomenon of fading. For a fixed receiver, the channel can be modeled as a linear time invariant signal. But if the receiver is not fixed, we cannot model a channel as a linear time invariant signal. Multipath propagation continue. Let's continue. And multipath can also cause large fluctuation in the received signal strength caused by the destructive interference or the different version of the same signal arriving at different time. So the received signal is the vector sum of different versions of the signal. And what are the different versions? The signal that are coming from different direction, different propagation delay, different amplitude, different phase, different angle of arrival, but they are copies of the same signal. These are the copies of the same signal. So if there is a destructive interference, the quality of the signal would be degraded. For a fixed receiver, the received signal strength would depend upon the frequency of the transmitted wave. That is, certain frequencies would be more favorable to the phase recombination than others. The presence of multipaths, therefore, give birth to the frequency fading visible on the transfer function of the channel. So multipath causes frequency fading. What does it mean? That for a fixed receiver, the received signal would depend upon the frequency of the transmitted signal. So there are certain frequencies that are more favorable to the phase recombination, but there are certain frequencies at which the corresponding quality would degrade, right? So when we talk about the transfer function of the channel, obviously, just a recap, I think most of you know that we have a transmitted signal x of t. Then we have impulse response of the channel, right? So when we talk about y of t in that case, that is the x of t getting convolved with h of t, right? So h of t is basically the impulse response in that case. But when we say y of f, for example, we have, and that this is the beauty of frequency domain. When we say y of f, we say x of f getting simple multiplication with h of f, where h of f is the transfer function of the channel, where h of f is the transfer function of the channel. So in the time domain, you have to do the convolution. In the frequency domain, you have to do the simple multiplication. So that was a recap of this. Effects of mobility. If we add the effects of mobility, the channel would evolve in time. We cannot say that the channel is linearly invariant. Channel is variant now. As the phase of the received signal is linked to the distance that wave has traversed, therefore distance with respect to the transmitting antenna and different reflectors and or scatters would impact the recombination of the multipath. Therefore, the received signal strength is also dependent upon the position of the mobile antenna in the environment. And therefore, whenever there is a mobility in the environment, it suffers from time varying fading. It suffers from time varying fading. So for the case when the channel was fixed, or when the receiver was fixed, we were getting the frequency fading. In case of the scenario where there is a mobility, we get temporal fading. So with different time, we get different kind of output, and therefore temporal fading. Talking about the Doppler effect, since we are talking about something in which there's a mobility. So obviously, whenever there is a mobility in the scenario, obviously, then we have to talk about the Doppler. When the transmitter or receiver is moving, the frequency of the received signal would not be same. When they are moving, the frequency of the received signal is higher than the source, if they are moving in the opposite direction, then the frequency is decreasing. You must have come across the example of a train arriving at a train station and train going away from the train station, right? A very common example in a high school related to physics, when you must have studied this Doppler. The frequency of the received signal can be written as Fc minus Fd, where where Fc is the source carrier frequency and Fd is the Doppler shift in the frequency. So whenever the object is moving, it will cause the Doppler effect. And you can see this car is moving in this direction, having some velocity v. So in that case, the corresponding Doppler effect, the corresponding Doppler frequency would be v over lambda, where v is its radial velocity, lambda is the frequency, and cos theta corresponds to the angle that it is making with this transmitted signal, right? So v is the radial frequency. So basically, whenever the object is moving, obviously it will have some non-zero velocity. It will cause a Doppler shift or the change in frequency. And since this Fd is non-zero, obviously the received signal's frequency would not be exactly the same as the source carrier frequency. That source carrier frequency will get added or subtracted because of this Doppler frequency, because of the movement of the object. And if the mobile is moving toward the direction of the arrival of wave, the Doppler shift would be positive, and negative in the other case.